Hello everyone, welcome to my channel. In this video, I would like to talk about Newton's laws of motion and applications. If you are new to this channel or you haven't yet subscribed, please support the channel by subscribing or inviting friends to subscribe and sharing these videos. It will help us grow the channel and put us in a position to develop many more videos and help as many students as we possibly can. All right, so let's go into the business for today. Newton's laws of motion and applications. I'm going to start with Newton's laws of motion. So let's start with Newton's first law. Newton's first law. Newton's first law. It states that a body at rest or in motion on a straight line and at constant velocity will continue to do so until an unbalanced force acts on it. So it states that a body at rest or in motion on a straight line and at constant velocity will continue to do so until an unbalanced force acts on it. So unbalanced, that word unbalanced means net or resultant force. So we're saying until an unbalanced force, or we can also say until a net force acts on it, or we can also say until a resultant force acts on it. Then that body will not continue to remain at rest or in motion in a straight line and at constant velocity. In other words, it may actually have its velocity increased or decreased, or it may change direction. Now, that's Newton's first law. Let's look at Newton's second law. Newton's second law. Newton's second law. I'm going to say something about Newton's first law after I've covered all the three laws. All right. Newton's second law, it states that if a net force, that word net means unbalanced or resultant, if a net force acts on an object, the object accelerates in the direction of net force with an acceleration that is directly proportional to net force and inversely proportional to the mass of the object. So let's state it again now. It states that if a net force acts on an object, the object accelerates in the direction of net force with an acceleration that is directly proportional to the net force and inversely proportional to the mass of the object. So that's Newton's second law. Now, I'm going to have to come back to this, but let me just briefly explain what the statement is saying. Maybe I should come back to it because this is the real deal as far as Newton's laws are concerned. Let me move to Newton's um, third law. So this is going to be page 2, number 3, Newton's third law. Newton's third law. Remember, we're talking about Newton's laws of motion. So we've stated the first law. We're going to come back and restate it. We've stated the second law. Now we want to state the third law. It states that if body A exerts a force on body B, body B exerts or will exert a force of equal magnitude, a force of equal magnitude. Let me change that one there. My hand is misbehaving. A force of equal magnitude. I'll come and fix that. Equal magnitude, but opposite direction. Don't say different, but opposite direction on body A. So it states that if body A exerts a force on the body B exerts a force of equal magnitude but opposite direction on body A. Notice we're using the word opposite direction. They're not different, opposite. So in other words, if body A exerts a force of 20 newtons east on body B must exert a force of 20 newtons west, because the opposite of east is west. Equal magnitude but opposite direction. Just be careful here to make sure that you don't say will exert an equal but opposite force. There is no such thing, equal but opposite, because two forces can only be equal if they have the same magnitude and direction. So in this case, we're talking about two forces that have equal magnitude but opposite direction. So these forces are not equal. They are different, because one would be 2,000 newtons east, the other one has to be 2,000 newtons west. So forces of equal magnitude but opposite directions. Right, that's Newton's third law. Now let's get back to Newton's first law. So I'm gonna say associated with Newton's first law. Newton's first law is what is known as inertia. And I'm going to define inertia. So inertia, definition of inertia. Inertia, you gotta have to master this one because it comes in exams. Definition of inertia. We define inertia as a body's resistance to change in its state of motion due to its mass. So basically we're saying if you're in a car, somebody is driving and they apply brakes, you shift forward a little bit and then settle back into your seat. And the reason why you shift forward a little bit is because of this concept or this idea of inertia, because your body would want to continue moving at the same speed that the car was moving at. But when the brakes are applied, remember a net force is applied, the body must not continue to move at constant velocity in a straight line like Newton's first law says, because of this idea of inertia. You move forward a little bit and then settle back into your seat. It's the same thing if you're in a train and somehow um, the brakes are applied, you shift forward a little bit and then get back into your seat. So that is the idea of inertia. Associated with Newton's first law is the concept of inertia. Let me give you another example. If the helicopter is rising at constant velocity, let's say 5 meters per second, and a stone is dropped, that stone initially moves up at 5 meters per second and then falls. The reason why it moves up initially at 5 meters per second, which is the same speed at which the helicopter is rising, is because of the concept of inertia, a body's resistance to change in its state of motion due to its mass. Right, let me say back to Newton's second law. Back to Newton's second law. This is the real deal. So we are saying here that we have, let's consider a block, and there's a force, net force, acting on this block. Let's say it's acting in that direction. Let's call it F net, written like that. And let's say the block has a mass of m and acceleration a going to the right, as shown in this diagram here. Basically, Newton's second law says that acceleration is directly proportional to net force, and it also says acceleration is inversely proportional to mass, like so. Now, the way that we combine these two mathematical relationships, this one and that one, is by multiplying the right side, this expression here, that constant value, net force, multiplied by the inverse, one reciprocal of mass. So we can combine these two as follows. We say acceleration is directly proportional to net force and inversely proportional to mass, written like this. Notice that I'm multiplying the two. Now, how do we turn this into an equation? From proportionality relationship into an equation, the rule says, the old syllabus, we used to call it in mathematics joint variation. Now that is removed from the curriculum if you are studying or watching this video from South Africa. So basically we are saying, for us to change from that sign to an equal sign, we have to multiply the right hand side by a constant. So then the equation changes, the relationship changes to acceleration is equal to a constant k, and notice this can also be written as F net over mass, like this. Right. Now, let me go to page number 3. I'm going to keep this one because it's critical. Yeah, page number 3. So basically what we're saying is this relationship here, experiments conducted have shown that the value of k is actually 1. So we're basically saying if k equals 1 there, we can say here, let me just put it down here. Experiments have shown that k equals 1. I'm not so much interested in the units. You can actually put the units there of the value of k, but k equals 1. Let's just focus on the magnitude. And if k equals 1, then that relationship changes to a equals 1 times F net all over mass. Now you will agree with me that this is basically F net, if I write the right hand side first, over mass is actually equal to a. Multiply both sides by mass, you have an equation that says F net equals mass times acceleration. So this is basically Newton's second law equation. This is how it is actually brought about. Right, so that's Newton's second law equation. So we are interested in net force, and then we multiply by, we say net force is equal to the product of mass and acceleration of any object on which the net force is acting. Just to remind you that net force is actually the sum of all forces acting on a system, or a single force whose effect is the same as all forces acting on a system combined. Let me just define it. So F net, we're saying this is net force. By definition, we say it is the sum of all forces acting on an object or a system. We can also say, alternatively, we define net force as a single force that has the same effect as all forces acting on an object or a system. That's the definition of net force. Now, we've stated Newton's second law. We are going to look at applications of this. But now that we are busy talking about forces, I want to talk about types of forces. So that takes me to page number 4. We'll come back to that. Page 4. I want to talk about types of forces. So we have number 1, we have what we call contact forces. These forces exist only when objects are in contact with each other. Examples of contact forces, we have tension, we have applied force, and yes, we have frictional force. You can also say we have what we call normal force. Normal force, we're going to define what normal force is, but these are the famous forces that exist due to contact. Right. Next, I'm just giving 3 examples there. The next type of forces, we have non-contact forces. And examples of non-contact forces, we have gravitational force, and then we have what we call electrostatic force, and we have also what we call magnetic force. These forces act even though there is no contact between objects, but these ones exist only when there's contact. Right. Now, there are very special forces in physics that I want us to look at, especially with regards to Newton's laws. And these are, let me just call them special force. Number 1, it will be frictional force. So let's look at this frictional force here in a lot more detail. So frictional force, there are 2 types of frictional force. We have one, let me just go straight to types. Let me just complete it. Types of frictional force. Types of frictional force. We have what we call static frictional force. Number 1, static frictional force. Now, static frictional force, I define static frictional force as it is a force that opposes the motion of an object just, underline that word there, just before the object starts moving. Some books say it is a force that opposes the motion of a stationary object. Of course, it's the same message. A force that opposes the motion of an object just before the object starts moving. That's static frictional force. That's a definition. The symbol for static frictional force, that takes me to page 5. Page 5. Page 5. The symbol for static frictional force is capital F subscript S. That's the symbol for static frictional force. And of course, it's a force, so it is measured in newtons as the SI unit. Now, let me move straight to the type of frictional force number 2, which is kinetic frictional force. Kinetic frictional force, we define it as, okay, so let me just go back here a little bit. We said static frictional force, it is the force that opposes the motion of an object just before the object starts moving. But we must continue and say, and I forgot to add this, and this is very critical. I've just remembered that it cannot be forgotten. Actually, we have to include it in the definition. And this force, which force are we talking about? This static frictional force. And this force always acts parallel to the surface on which the object sits or is placed, on which the object, let's just say is, on which the object is. So let me just repeat this. I'm saying static frictional force, by definition, it is a force that opposes the motion of an object just before the object starts moving. And this force always acts parallel to the surface on which the object is or placed or is placed. Right, let's move on. I said the symbol for static frictional force is Fs. Kinetic frictional force, we define it, and this is what led me to remember that part of the definition of static frictional force. So we're saying kinetic frictional force, we define it as a force that opposes the motion of a moving object, not an object just before it starts moving, but this time the object is moving. It's a force that opposes the motion of a moving object and this force always acts parallel to the surface on which the object is moving. So kinetic frictional force is a force that opposes the motion of a moving object, and this force always acts parallel to the surface on which the object is moving. That's the definition of kinetic frictional force. The symbol of kinetic frictional force is Fk. That's the symbol of kinetic frictional force, Fk. And obviously, kinetic frictional force is also measured in newtons because it's a force. All forces are measured in newtons except what we call electromotive force, which actually is not a force but performs the function of a force. It's measured in volts. We will look at it when we start looking at electrodynamics as well as internal resistance. So, but in this case, we are saying kinetic frictional force. It's a force that opposes the motion of a moving object, and this force always acts prior to the surface on which the object is moving. The symbol for kinetic frictional force is Fk. Now, I want to define another very important type of force. Remember, we're coming from frictional force here, and I said these are special forces. Frictional force, two types we've mentioned, and I want to talk about type of force number 2, special type, normal force. Normal force, we look at the definition of normal force. So we define normal force as it is a force that the surface exerts on an object. Let me rewrite that. Normal force. What is it? It is a force that the surface exerts on an object placed on it, and this force always acts perpendicular to the surface. So we are saying normal force, it is a force that the surface exerts on an object placed on it, and this force always acts perpendicular to the surface on which the object is placed. That's your normal force. The symbol for the normal force, my hand is misbehaving there. The symbol for normal force is either F subscript capital N or just capital M. So F subscript capital N or just capital N, that's the symbol for normal force. And obviously normal force is also measured in newtons because it's a force. Remember the definition? It's a force that the surface exerts on an object placed on it. So if you put a box on a surface, on a table, the force that the table exerts on the box is what we call the normal force, and that force must always be perpendicular to the surface of the table. Right. So now we've defined all special forces. I want to go back and talk about frictional force a little bit more mathematically. That takes us to page 6 now. Page 6, I want to talk about frictional force. So, and we are talking about static frictional force and kinetic frictional force. It turns out that static frictional force is directly proportional to normal force. Static frictional force is directly proportional to normal force, and kinetic frictional force is also directly proportional to normal force. Now, so again, to change these mathematical relationships into equations, we basically are going to say Fs for static frictional force is equal to mu s times Fn. Notice that mu s is a constant of proportionality. In this case, it has a special name. We call it coefficient of static friction. And also here, to change from that relationship, mathematical relationship, into an equation, we're going to have mu k times Fn. I must say that this is exactly equal to coefficient, or is known as coefficient of static friction And so it is read as mu s. Please take note of that. Read as mu s. And we're also saying mu k is coefficient of kinetic friction and it is read as mu k. Read as mu k. Now, I want to talk about these equations a little bit more. Now, if you notice here, Fs equals mu s Fn, we can say mu s is actually equal to Fs all over Fn if you divide, make mu s subject to formula there, and mu k is actually equal to Fk divided by Fn. Now, you can actually see that this one and this one, these two guys are what we call, these are ratios. So we can say, therefore, mu s and mu k have no units, because they are ratios, They're going to ask you, explain why the coefficient of kinetic friction has no units. The answer is because it's a ratio. Why mu s has no units? Because it's a ratio. And I want to say straight away here that in most cases, the static friction force is greater than kinetic friction force. In fact, this is the maximum frictional force that an object can experience just before it starts moving. And from here, we can actually say that by definition, this one here is mu s times F normal. If you are considering one object, this will be greater than mu k times F normal. Where am I getting these from? I'm getting them from the definition up there. And when you cancel out the F normal, it turns out that coefficient of static friction is always greater than coefficient of kinetic friction. Take note of that very important result there, right? We will look at how you can determine that on an incline. But for now, I just want to talk about motion on a straight line and on a horizontal surface along the x-axis, or if you like, along the y-axis. Right, now, remember, we are saying back here, I want to focus on this a bit more, and then I'll turn back to that. Now, coefficient of kinetic frictional force equals coefficient of kinetic frictional force, which is mu k times the normal force. Now, let's look at a force. Firstly, I want to look at how to determine that when an object is being pulled or when an object is being pushed. Please take note of that. This one here. When is kinetic frictional force greater? Is it when you are pushing an object or when you are pulling it? Let me write that one down. That's page number 6. So this is page 7. When is kinetic frictional force greater? Is it when an object is being pulled or pushed? This is what we want to answer. We want to answer that question by looking at a force as a pull first. So now we're going to look at force as a pull. Remember, we define force as a pull or a push. Force as a pull. Now let's look at an object placed on a horizontal surface. And this object is being pulled to the right by a force F at an angle of theta. And obviously, we're considering frictional force here. So we're talking about a surface that has frictional force. So you expect frictional force to be acting opposing motion in that direction. Now, there are two things I want to talk about here in this scenario. I want to talk about what we call a free body diagram and a force diagram. So please take note of the difference. Let's look at free body diagram straight away. Free body diagram versus a force diagram. They may ask you to draw a free body diagram or a force diagram. Now, in a free body diagram, we have a dot representing the box, and obviously there is going to be, because sitting on a surface, we have a normal force acting vertically upwards. Let's call it normal force F subscript N, and we have gravitational force in that direction. Let's call it W for weight, which is equal to actually Fg, and that equals mass times gravitational acceleration. And then we have frictional force acting in that direction horizontally, and this, assuming this object is moving, that will be Fk. And then we have applied force at an angle, that is your applied force F at an angle theta. Do not forget to say where Fn equals normal force, Fk equals kinetic frictional force, and then we have W or Fg equals weight or gravitational force, gravitational force, and then we have our F, which is applied force. So that's a free body diagram. Now let's look at the force diagram. Now, when you're looking at the force diagram, we are going to have a box. Our box is sitting on a surface, and there's a force applied on it, pulling it to the right, which is the applied force. Let's respect the angle theta, and there's a force that the surface exerts on the box. It is in that direction, so that's F normal force. And then there's a force that the box exerts on the surface. It doesn't really matter whether you draw this to the right or left. This is the force of gravity, Fg, which is actually equal to mg, and we know that this is weight, W equals this. And there's a force on the surface there, and that's your frictional force, kinetic frictional force. Please take note of the force diagram and the free body diagram. Watch frictional force parallel to the surface on which the object is moving. Gravitational force starting from the center, or we call it center of mass of the box, just in the center there, pointing downwards. Normal force from the surface through the object, obviously going up there, and applied force drawn like that. If they ask you to draw this, you are still going to say where this is the story. Fn equals that, and all the way up to down here. Right, so there is, you have your free body diagram, and then you have your force diagram there. Now, remember, we're talking about force as a pull. So I want to look at this free body diagram. In this case, I'm going to turn it around and draw something that is not a free body diagram, because in a free body diagram, you're not allowed to have your applied force and its components in the same diagram. It's either you have components of this force or you have that force, and it is recommended that you must have that, not its components, in a free body diagram. But for analysis purposes, I'm going to draw the components of this, the horizontal component and the vertical component, in the same diagram. Right, so let's take, that takes us to page number 8. Page 8, I want to talk about a force as a pull. We are basically saying, let's have the components in the same diagram. So this is what I'm going to have. This is F in the X direction, and that's going to be F in the Y direction. That angle is on 90 degrees, and there's your theta. And then we have normal force there, F normal. And then we have frictional force in that direction, Fk. And then you have gravitational force. down there, Fg, which equals mg. Now you have your F there. Now, so what we're saying now is, please take note that this force here is supposed to be there, but because these are coplanar forces, I can move it around without changing magnitude and without changing direction. So it is supposed to be there, and I move it across. Let me just show you something here, what I'm trying to say. Get a page, if I may, down there. Right, so what I'm saying now is, um, when a force, applied force, is actually in two dimensions like this. It's two dimensions because I'm talking about we can have two components of this force in the x-axis and in the y-axis. This is how it's supposed to be all the time. So because these are coplanar forces, I can move this across, move it across to there, so it's gonna be in that place. Why am I doing that? So that I'm able to form a right angle triangle. And then I can work out these forces in terms of that angle there by using trigonometrical ratios. All right, so that's why we're saying this force is here and we move it across like that. Now let's talk about this force and that force, especially that force, because I'm talking about I want to talk about frictional force. I'm not worried so much about horizontal forces. We'll look at horizontal forces in another video. In this video, I just want to talk about frictional force. Now, so we are basically saying the ratio of the opposite side to the hypotenuse is actually equal to sine of the angle. So basically we're saying Fy divided by F equals sine of theta. Opposite of hypotenuse equals sine of the angle. Multiply by F both sides, you're going to find Fy to be equal to F sine theta. This is critical because now when we look at this object, the assumption is that this block is moving horizontally to the right, is not jumping up and down, and therefore the normal force plus the vertical component of applied force, the normal force plus vertical component of applied force, the two, when you add them up, because they are acting in the same direction, so we add them up, the sum of the two, their magnitude will be equal to the magnitude of gravitational force, because this thing is not moving up and down, it's moving straight on a horizontal surface. So what are we saying? Net force in the vertical direction is actually equal to 0. So we are saying the sum, sigma notation, of net forces, sum of all forces, I'm going to just write F, because sum means net, sum of all forces in the y direction is equal to 0. I'm coming back to fix that, equals 0. Hopefully I don't forget this. So what does this mean? It means that if I take up as positive, then I'm going to have the net force at normal force will carry a plus sign because I'm talking about up as positive. This will be positive. I'm summing up because of the sigma notation means sum. And what is sum? Remember, we're coming back to the definition of net force. How did we define net force? If you allow me to move back so that I remind you, if I move back just a page or two, I like to do that so that no one forgets these things. Do I have it here? Yes. How did we define net force? Here's the definition of net force. It is the sum, there you go. It is the sum of all forces acting on an object or system. So there is your sigma notation representing sum. Sum of all forces in the y direction equals 0. This thing is moving horizontally, not jumping up and down. So it means if I take up as positive, these two forces must be positive, but I'm summing them up because of the definition of net force. So I'm saying this Fy must be positive, but I'm adding, if up is positive, down must be negative. So I'm supposed to say minus Fg. The answer must be equal to 0 because net vertical force is 0. Now, from here you can see simple algebra. It will say that normal force is actually equal to, take this one to the right hand side, you're going to have positive Fg and then minus Fy. But what is Fg? It's mg. So F normal equals mg minus, what is Fy? Well, Fy is F sine theta. F sine theta. Now, let's go back to the definition of frictional force. How did we define frictional force? kinetic frictional force particular. Let me just take you to that page where I defined kinetic frictional force. Kinetic frictional force, I think it must be on this page here. Here we go. If you check page 6, kinetic frictional force, there is the product of coefficient of kinetic friction and the normal force. So in the place of the normal force there, I'm going to put this expression. But let me remind you, but Fk is equal to mu k times F normal. Now in that place, I must put that expression. So that takes us to a very important equation. Kinetic frictional force is equal to mu k, open brackets, mg minus F sine of theta. I'm going to put this in a rectangular box, and I'm going to put the minus sign, preferably in a red. I have a red pen here. Here we go. So I'm going to put that in red. I want you to see what happens when we change now from pulling to pushing. Take note of that minus sign. Remember, we looked at a force as a pull. Now let's go to page 9. We're going to look at a force as a push. Page 9. Just want to make sure that we don't go up to 1 hour here. Page 9. We're talking about force as a push. Now we have a block which is being pushed instead of being pulled, sitting on a horizontal surface. This block is being pushed at an angle. Let's call that angle theta, by a force F, which is our applied force. Now notice that this force has two components, as vertical component and horizontal component in that way. Now, if I move this force down there, you can actually draw this force down from here, going down that way. I hope you catch what I'm saying, because these are coplanar forces. I can move them around, but there is frictional force on the surface there, opposing motion, right? So it doesn't really matter whether you draw it here, but it's best maybe to draw it on this side here. There's frictional force, but you see, when we look at the free body diagram, it will be different. A force diagram, you have to draw it on the right hand side there. So let me put it this side. There's a frictional force, opposing motion. Doesn't really matter where you place it, because these are coplanar forces. You can move them around without changing direction and magnitude. And obviously, there's also a normal force up from the surface, and there's gravitational force pushing it down. Now, how does a free body diagram look and a force diagram? So, free body diagram, and then we have force diagram. Now, what I was saying is, I think you understand it better if I put it on a separate page. What I was saying is, we have a box, and you have a force like this. This force has horizontal component, has vertical component. Now move it down. When you move it down, it will come. Remember, this must be a straight line like this. You have your dot there representing a body, this one. That force will be acting in that direction, and frictional force obviously is opposing motion. And you can see that these angles here are going to be vertical opposite angles, so that will be your theta. And this force will be that force. That force vertically will be in that position there. And because these are coplanar forces, I can move this force across to that side there, that side. And it's important because I want to have gravitational force there, Fg. So I will have that component, and that force, our original force. Obviously, we're not going to put these two in our free body diagram, but there's a normal force here, you must remember that, and there's frictional force. So how does a diagram look then for a free body diagram? It looks like this. Watch this. There is, I almost forgot there. We have gravitational force in that direction, and then we have normal force up there, F normal, and then we have frictional force in that direction, Fk. We're assuming the object is moving. And watch this, there's a force in that direction. This is our applied force F. And if you like, that is going to be our theta. So this is how your free body diagram is going to look like when an object is being pushed. Notice what I did here. I moved this down. Moving it down means that that angle is equal to that angle. Vertical opposite angles must be equal. So that angle there is down there, and then you have this force here, and of course the horizontal component will be there, vertical component is supposed to be down here, but we move it across because these are coplanar forces. So, but remember, in a free body diagram, you can only have the original force and no components, right? Let's look at the force diagram. The force diagram, we're going to have that block there on a surface, and obviously there's a force pushing in that direction. We respect the angle, that's our theta, that's our F. And frictional force, remember this is the surface, horizontal surface. Frictional force is there, and obviously you have, check this out, gravitational force in that direction, and then you have normal force from the surface going up. This is F normal, and this is Fg, which is weight, and that's applied force F, and that's your surface. This is the force diagram, and that's a free body diagram. But for analysis purposes, I want to redraw this. I want to redraw it. I want to redraw this for analysis purposes. I'm going to have this one here, and I'm going to have the component horizontal, and then I'm going to have my gravitational force Fg, which is equal to mg, and then I'm going to have my force F in that direction, and then I'm going to have the vertical component of that acting downwards, Fy, horizontal component Fx. Then it's going to be my normal force there, F normal, and then I have frictional force there, Fk. Notice something now. This is still my theta, and we're still saying this is actually equal to F sine theta. Convince yourself. I didn't talk about that, but we know that this is going to be F cos theta. If you use trig ratios, ratio cosine, this is what you're going to get. But I'm not focusing on that horizontal motion for now. In terms of forces, I'm focusing on vertical motion because my emphasis is on calculation of frictional force. Right. So now let's look at this angle. Obviously is 90. Now notice now, if we say this net force in the y direction is 0, we're basically saying, suppose we take up as positive. If we take up as positive, we're going to have only one force that is positive F normal in brackets. I'm going to say add because of sum. Sigma notation means we're summing up all the forces. But now, watch something. The Fg must be negative because if up is positive, down must be negative. Let me put there, if I'm saying up is positive, down must be negative. It means these two guys will be negative, both of them. But I'm summing them up because net force is the sum of all forces acting on an object or system. So this is going to be minus Fy. And what is this equal to? 0. Now, make F normal or normal force subject to formula. These two guys must go to the other side, or add these two on both sides. Add Fg and Fy on both sides. You're going to have F normal equals the sum of these two on the other side, which makes sense because we're basically saying when you add these two up, the magnitude will be the same as magnitude of Fn. Let's go to page 10. Page 10, and hopefully I can finish off in this video on page 10. Page 10, we are saying now, watch this. I'm saying now, take these two guys the other side. You're going to have, hopefully you can see what I'm writing. Oh yeah, you can. So we're basically saying Fn is going to be equal to Fg plus Fy. What is Fg? Mg. What is Fy? F sine theta. What is this one here? It's F normal. Now, what did we say? But kinetic frictional force is mu k times normal force. So in that place now, I must put that. Therefore, Fk is equal to mu k open brackets, mg plus F sine theta. Now, like I said in the previous one, like I did in the previous one, I'm going to put a plus sign here in red. Now so this is, remember, this is when an object is being pushed. The question we're answering is, when is kinetic frictional force greater? Is it when you're pushing an object or when you're pulling it? Now, when you're pushing, there's a plus sign there. When you're pulling, let's check the page that I have. Hopefully I can find it here without wasting time. I've got a couple of pages here. Let me just quickly look for it. Here we go. I got it. There it is. So this is for pushing and that's for pulling. Now you will see that here the two numbers are subtracting and multiplying by k, mu k. Here the two numbers are adding. Obviously this value, the value there should be bigger than the value here. Remember, this is for pushing and this is for pulling. So when you're pulling an object, frictional force is smaller than when you're pushing it. And that's why it is easier to pull objects than to push them. For a high school teacher, you would say that's why most of us like to pull learners to class and not to push them to class. Just joking. But yeah, so the value of Fk when you're pushing an object is actually greater than Fk when you're pulling it. Right, I'm going to stop here in this video. In the next video, we're going to look at applications and we'll look at the towing system, and we'll also look at the inclined plane, the lift, and many other applications of Newton's second law. Yeah, so if you're new to the channel, like I've said at the beginning, support us by subscribing and inviting friends to subscribe. I will come back with many more videos on mechanics. I have started now with Newton's laws. We'll go on and look at many other topics in physics. All right, see you next time.